So we're happy to have Ofir Gorodetsky from Tel Aviv tell us about the distribution of square-free integers in short intervals.
So thank you, Sarah, Sean, and Sean for the invitation to speak here and for the organization of this nice webinar. And today I want to talk to you about square-free integers in short intervals. This is a joint work with Kaisa Matomäki, Radziwill and Brad Rodgers, and you can find it on the archive. And the slides will be shared in the chat, so you don't have to, I don't know, print screen or something. So let's start. Our object of study will be square-free integers. A positive integer is square-free if it is not divisible by a square of a prime. In other words, it is a product of distinct primes. So 1, 2, 3, 5, 6, 7, 10, and 11 are square-free numbers, but 4, 8, 9, and 12 are not. And a natural question is to understand how many square-free numbers are. So let's try to do it at least heuristically. Let nx be some random number between 1 and x. And let us ask what's the probability that it's not divisible by a given square p squared. And this is asymptotic to 1 over 1 minus p squared. And if these events were independent, which they aren't, then we would have that the probability of being square-free would be the product of these probabilities, which is this infinite product which converges to a positive number. And before I'll talk about how to formalize this argument, this classical argument, I want to show some graphs. Okay, sorry, I'll first say something about the constant. So Euler already knew that this infinite product is 1 over zeta of 2, where zeta is the Riemann function. And you also know the exact value of zeta of 2, it's 6 over pi squared. So this heuristic argument tells us that the density of square-free should converge to 6 over pi squared. In particular, they have a positive density within the integers, as opposed to, say, primes. So now I'll show some graphs. So what do we have here? Here we plot the number of square-free numbers up to x as a function of x. And you can see that it's very linear. And the slope is close to 0.6 something. And you can look at the difference between the number of square-frees in this approximation of x over zeta of 2. And you can compare it to this graph of x to the 1 over 4 in blue. I'll explain later why I specifically chose the x to the 1 over 4 as the sort of upper bound or order of error. But you can see that the error is very small, at least up to 10 to the 5. So now I'll talk about formalizing this probabilistic argument. And an object that will be recurring in this talk is the mobius function. So let's recall its definition. It's a function of the positive integers. So if the number n is not square-free, so it's 0. But if it's a product of k distinct primes, it will be minus 1 to the k. And this function allows us to do inclusion-exclusion arguments in number theory very conveniently. So this indicator function of square-frees that we're studying, we can express it using the mobius function. Specifically, it's the sum of mobius d, where I sum over all the squares d squared that divides my number n. So how does one verify this formula? One way is to interpret it as an inclusion-exclusion, where we have the events that my number n is indivisible by p squared, and I'm intersecting these events. That's one way to look at it. Another way is to see that these two functions are multiplicative in n, and then you just have to check equality on prime powers. So, and you can also prove this by Dirichlet comparison of Dirichlet's theory. So whatever whatever way you choose. But this identity will be very important in this talk, so that's why I mentioned these ways of proving it. And another way to maybe think about this function as a Dirichlet convolution of two functions. One, which is the constant function 1, and alpha, which is a function that's supported only on squares. And on a square, its value is mobius of square root of the square. It's just another way of writing this formula. And with this formula at hand, we prove that the density of square frees is 1 over zeta of 2 as follows. We want to sum S of n for n up to x. Then we plug this sum over squares, and we do the most common trick in number theory, which is to exchange the order of summation. So instead of summing over d on the inside, we sum over d on the outside. And the inside, we have to sum over multiples of d squared. And the number of multiples of d squared is roughly x over d squared. But of course, there's an error that should be paid. I called it e. And this e is mobius of t times this fractional part of x over d squared. These squiggly brackets are the fractional part of this fraction. So I claim that this is essentially gives us what we need. Why? Because this error term is clearly big of square root of x. There are square root of x terms and they are bounded. And this finite sum converges to the sum of mobius d over d squared, where I sum over all these. And this sum is actually 1 over zeta of 2. This can be verified by checking Euler products, say. So we know that the square frees have a positive density formally, and we use this nice inclusion-exclusion formula. And next, I want to talk about square frees in short intervals. So what do I mean square frees in, oh, sorry, one last thing I wanted to say is that we can ask how small this error is. And I want to give a very informal heuristic argument, which is that we have square root of x terms in the sum, and the terms are somewhat random due to the presence of the Mobius function. So one might guess that the error term e is the square root of x, so x to the 1 over 4, maybe up to some correction, to some lower order terms. And in the next slide, I'm going to state maybe a more general prediction. So what's a short interval? A short interval is an interval of the form x to x plus h. H grows to infinity squared than x. So if h was exactly x, we would call it a full interval. So a conjecture, which I haven't seen it stated in this form in the literature, but for instance, it was stated for arithmetic progressions by the same sort of heuristic, is that the sum of this indicator function over this short interval of length h will be h times this density of square frees, and that there will be an error term which is essentially h to the 1 over 4. And this should hold as long as h is greater than some arbitrary power of x. So for instance, if you take h to be exactly x, you get that the error term when you sum in a full interval should be x to the 1 over 4 roughly. So what is known about this conjecture? So the error term, at least in this sort of optimal shape, is not known for any value of epsilon. Even so, for small h, for big h, there is no h for which we know that the error term is so small. But there is a range of epsilon where we know the correct asymptotics. So what do I mean by the correct asymptotics? I mean there is a range of h where we know that the number of square frees in the interval of size h will grow like h over zeta of 2. So in the previous slide, we've essentially seen that the count of s in a full interval can be given with an error term of square root of x. And this will already give you an asymptotic result when epsilon is greater than 1/2. Tolev showed that we have this asymptotic formula as long as epsilon is greater than 1 over 5. And Granville and Antin showed that the asymptotic holds for the full range for all epsilon greater than 0 under the ABC conjecture. And I want to emphasize that for small epsilon, we don't even know that this quantity is positive. We don't know that there exist square frees in very short intervals. But in function fields, it is known by work of Carmol building on a work of Poonen. We do know that at least in the function field setting. So that's the conjecture. And now I'm going to introduce the variance of square frees in short intervals, which will allow us to give some evidence towards this conjecture. It's a way to introduce some averaging into this conjecture. So what is this variance? I choose some random number between 1 and x, uniformly at random, and I form this random sum. It's just the number of square frees in this interval from u to u plus h. And I want to study it. So it's a sum of over an interval of size h, but the starting point is random. And again, h will be something that's less than x, but grows at least some power of x. So computing the expected value of this random variable is essentially computing the density of square frees. And it's easy to see that it will grow like h over zeta of 2. But what about the variance? So if we can say that the variance of this random variable is small, for instance, if we can show that it grows like square root of h, then that will tell us that at least for most values of u, the count of square frees is very close to h over zeta of 2, where by very close I mean with an error term that's roughly the square root of the variance. So knowing the variance will give us something about square frees in most short intervals. So what's known about this variance? So there is a range where it was computed by Hall in 82. It showed when h is not too big, specifically h is smaller than x to the 2 over 9, we have an asymptotic formula for the variance, a very simple one. It's a constant times square root of h. And the value of the constant is explicit, but we won't need it at any point of the talk, so you don't have to look too much into the value of the constant. I'll try to understand, at least heuristically, why is for smaller h, the variance is easier to study, like why he had some barrier. We'll see formally later why it's a barrier, but at least heuristically, an interval of size x can be seen as x over h disjoint intervals of size h. So the smaller h is, the more non-overlapping intervals of size h we have in our range. So there is more averaging, and extra averaging is always helpful in number theory and I guess in every field. So that's why his proof only works up to some power. And the talk today will be about how to push beyond this power. But first I want to tell you about his proof method, about Hall's proof. So the proof is somewhat, I call it direct. He expands the definition of the variance. And once you expand it, you obtain h squared sums of this form. What is this sum? It's a correlation sum. So it's an indicator function of n plus I and n plus j being simultaneously square free when n runs between 1 and x. And I have h squared sums because I have this sum occurring for every value of I and j between 0 and h. And this might look at as a hard problem at first because, for instance, the twin prime problem is also about some kind of correlations, but this problem is substantially more easier. And in fact, there are asymptotics for these sums dating back to Karlitz and Mirsky, I think from the 40s. And they proved that this sum grows like a constant times x, which makes sense because the events that n plus I and n plus j, each of them being square free, have positive probability, but it's not clear that they are, how dependent are they, but it's not surprising that it grows linearly, and they obtain some power saving. And this is uniform. The error term is uniform in the values of I and j up to x. So once we have this formula of Karid-Samirsky, we can just plug it in our expansion of the variance, and then we just need to sum these constants, aij. And summing these constants is a technical computation involving the Dirichlet series, but it's nothing special. And we see why it becomes harder and harder for larger h, because for larger h, we accumulate more error terms. So let's try to see what are the limitations of this method. So if you inspect the proof of Hall, you see that he essentially proves the following. If the error term in this correlation sums is x to the theta, then you obtain the correct main term in the variance, but with an error term that grows with theta. It has this shape. So if we plug in theta equals 2/3, and we ask when is this error term is smaller than the main term, that we obtain exactly the range of Hall. And there has been some improvement on the value of theta a few years after Hall's work. Sun, building on work of East Brown, improved 2/3 to 7/11, which gives a slight improvement to this range of 2/9. And notice that for I equal j, we know that the correct error theta should be 1/4, or we expect that the correct theta should be 1/4. So the most optimistic conjecture would be that this error term is in this error term we can take the value of theta to be exactly 1/4. And if you plug here theta equal 1/4 in this error term, and you see when is it smaller, then you obtain a result in the range of h smaller than square root of x. But again, I want to emphasize that this is completely open, and the best known theta is 7/11. So now I want to mention some recent work in the function field setting. So Keating and Rudnick studied the variance of square-free polynomials. Basically, they translated the problem in the function field setting to a question about zeros of L functions, and then used some equidistribution results coming from algebraic geometry to related question about random matrices. And their computations led them to believe that Hall's result should hold in the entire range. So this asymptotic of c times the square root of h, they expected to hold for h as large as x to the 1 minus epsilon. And again, they proved a version of this in the so-called large Q limit, where the base field grows and the other parameters are fixed. So now that we've seen Hall's result and mentioned Keating and Rudnick's work on conjecture, I'll mention our main result. So our main result is as follows. So unconditionally, we improve the range of Hall's results up to h, which grows like x to the 6/11, which goes beyond square root of x. So you can say that this result exploits cancellation in these error terms in the slide about Hall's method of proof. Now there is the Lindelof hypothesis, which I will mention later. I will define later for those who are not familiar with it, and this will give us a result for h up to x to the 2/3. And if we assume the Riemann hypothesis, which is stronger than Lindelof, or at least not weaker than Lindelof, then we can obtain the correct upper bound in the full range, but not asymptotics. So this is our main result, and this will be the rest of the talk will discuss some of the ideas that go into the proof of this. I also mentioned that we have at least the two first parts. We have analogs for in the arithmetic progression setting, which was also studied by Nunes, by Bloomer. But I'll stick here to short intervals. And maybe before I delve into the proof, I'll mention that this paper of Keating and Rudnick was somehow the starting point of this investigation, because when I looked into it, I saw that when they modeled the zeros of the zeta using eigenvalues of random matrices, you can see that at least in some range, this can be proved in the n limit as well. But it took a lot of work with Kaisa, Max, and Brad to actually transport these ideas to the integer setting. But somehow the function field setting was how this started, and some of the ideas are clearer there. Okay, so now I'm going to delve into the ideas behind the proof. So recall what is our function that we're studying, this indicator of square frees, which can be written as this Mobius sum. So I write here the Mobius sum a bit different than in the previous slides. I write it as Mobius of D, where I sum over all the ways to write n as a square times m. And the variance we are after can be written as an integral where x runs between capital X and 2x. We have this short sum minus this expected main term. In the previous slide, I may have defined x as being between 0 and x instead of x and 2x, but it is immaterial. It will be just more convenient that way. And here I rewrite in the second line, I rewrite this sum as the sum of this square times m. And the thing that I will focus most on in this talk is to see actually how to control the contribution of large d's. What do I mean by that? If we only sum here over these in some, let's say, dyadic interval to the decay up to the k plus 1, we can try and see what's its contribution. Of course, it's natural to do it dyadically because you might guess that different d's will give different contributions. So it's not wise to do all of them simultaneously. So in the next slides, we'll try to just contribute or control the contribution of these in different ranges. And what we'll end up seeing is that large d, and by large d I mean d such that d squared is larger than slightly larger than h, we see that these large d do not contribute to the variance. What do I mean by that? We expect the variance to be order square root of h, and these guys, this large d will contribute less than square root of h, and we can just throw them. And after we throw them, we just have to deal with this sum where we go over only over small d, and this turns out to be a much more easier task. And I will not talk, I'm not sure if I will have time to talk about studying really the contribution of the small d's, but somehow the hard part is controlling the large d's. So in the next slides, we'll try to study what is the size of this integral when I restrict my attention to small d, or for d in some interval. Another way to think about it is replacing this alpha in this convolution of alpha convoluted with 1. We are replacing alpha with alpha restricted to some dyadic interval. So any questions before we are delving into some gory details? Any questions from the audience? Just checking the time. Just also want to make sure that I'm being heard. Okay, thank you, Sarah. Okay, so in the next slides, I'm going to talk about how we're going to relate this somehow to the generating function of S for the Dirichlet series of S, because Hall's proof stayed only in physical space, meaning it didn't use properties of the generating function of S. And it turns out that doing so will be beneficial. So let's get right into it. So how we use this notation where d squared, I write it like tilde d, tilde capital D. This will mean that d squared is between capital D and 2 capital D. This will be the meaning of this notation. It's not asymptotic to, it's just of order of magnitude d. So instead of summing over all these, as I said, I'm summing only over this kind of these of this order of magnitude, and I no longer subtract h over zeta of 2. I subtract the part of the chunk of 1 over zeta of 2, which is supposed to cancel this arithmetic sum. Okay, so that's the object we're trying to bound. So let's introduce this function a of x. It's just a sum of an arithmetic function. So d squared is of order capital D, and I have this Mobius weight. And then I sum over m such that d squared m is at most x. And I subtract again what I expect will be the main term of this creature. So once I introduce this function, we can write our integral as an integral of a of x plus big H minus a of x. And I will want to somehow relate a of x to the underlying arithmetic function that we sum here. So we introduce this Dirichlet polynomial m of s, which is a sum of Mobius d over d squared to the s, where again I sum over only in a sum dyadic interval. And by Perron's formula, we can see that the previous function we defined ax is essentially the inverse Mellin transform of m of s times z of s. You don't need to understand what these words mean. You just need to be familiar with Perron's formula. So Perron's formula tells us that if we want to sum a certain function up to x, we can do it as follows. We integrate its Dirichlet series against x to the s over s. So we do it over this line 2 plus IR, because there everything converges nicely. And why do I have the integral of m times zeta? Because the arithmetic function I sum here is exactly 1 convoluted with Mobius of square root of d. So it's a convolution of 2 functions. One is the generating function zeta, and the other is the generating function m of s. And the left-hand side is not quite a of x, because we want to somehow subtract the main term. But notice that zeta has a pole at s equals 1. M doesn't have any pole because it's a polynomial. So we can shift the contour of integration to the half line. When we shift it, we pick a pole. And this pole can be shown to be exactly the main term subtracted in the previous slide. I will show it in a second. But what we end up seeing is that a of x, well, I do a change of variables because it's nicer to work with integrals over R. So we have this integral of m on the half line, z times zeta on the half line, times this x to the 1f plus it over half plus it. I just want to remind you what was the main term. So the main term was this x times Mobius of d over d squared. So when you shift the integral to 1/2, you exactly pick this main term. And a general principle for this talk is that you don't really have to follow all the specific constant and expressions that will appear. I mostly want you somehow to get the ideas and the toolbox of the analytic number theory that went into play here. So it's okay if you miss some small technical details. Okay, so I have this formula for a of x, and it's very similar to a Fourier transform because I have this factor x to the it. So it's very similar to a Fourier transform of m times zeta on the half line, but not quite, because in the Fourier transform I have x in the exponent. So that's not a big deal. We can just do a change of variables, and this will look like a Fourier transform. So once we do this change of variables, replacing x by e to the x, and do some subtraction, we have this observation, which I think appeared first in the work of Selberg when he studied variance of primes in short intervals. So the observation is that if I take this a of e to the delta plus x for some fixed delta that we'll choose later, minus a of e to the x, divided by e to the x over 2, we really get a Fourier transform of this Dirichlet polynomial times zeta function of the f line times these somewhat annoying factors. Why do we have this subtraction? Because we actually want to, why do we take a difference? Because we want to study a problem in short intervals. We want to know what happens between x and x plus h. currently we're studying what happens between e to the x and e to the delta plus x, but a change of variables will lead us to the quantity that we're really after. So at this point, where we related our arithmetic object to this to its generating function, we can apply Plancherel. So the integral of this creature squared will be the integral of this creature squared, and we'll see that this is the integral that we want to bound, and we're going to throw a lot of tools from actually classical analytic number theory on it. So there will be not will be actually quite classical ideas. So I remind you that we wanted to study the object on the left-hand side. We're currently able to control a slightly different object, but a lemma of Safari and Vaughan allows us to move from one object to another, although at the cost of losing asymptotics. But that's fine, because I told you that I'm just trying to show that the large D are negligible. So this lemma of Safari and Vaughan tells us that we can move from the setting when we're interested in short intervals of fixed size h to this other setting where our intervals are of size theta u. So they're not of fixed size because u varies, but it will always be of order x theta, and theta is of order h over x. So this interval is still of order h, it just shifts in time, shifts with time. Okay, so with this lemma at hand, we can just do a change of variables on the right hand side of the lemma, call u e to the x, and we also want to choose our theta appropriately. We want to choose 1 plus theta to equal e to the delta to match with the previous slide. And once we do this change of variables, choose this value of theta, what we end up needing to bound is this big thing. X times this integral of these Dirichlet polynomials times zeta times this finite factor. You may ask, where did this factor of x came from? It basically came from doing this change of variables e to the x equals u. Again, it's not important to really for you to keep track of the specific powers of x that pop up. And I want to convince you that the action in this integral happens for small t. Why is that? Well, this factor in the numerator is bounded, and the factor in the denominator decays like 1 over t squared. M is just this Dirichlet polynomials with small coefficients. In fact, it's bounded as well. And zeta, well, we have this subconvexity estimates that tell us that this grows smaller than some very concrete power of t. So the action here is definitely happening for smaller t's, meaning that we can sort of cut it off at some sufficiently large power of x. Specifically, here I will concentrate on the integral up to x over h, but the techniques that I'm showing you will work beyond x over h. And why it's natural to cut this at x over h? Because in that range, recall that theta is essentially h over x. So when we are going with t up to x over h, we can say that this factor is basically of order delta squared. So we can just put it outside as delta squared. So at least for t sufficiently small, up to x over h, we can just replace this factor by delta squared. And trust me that higher t's can be either held in similar ways as I will show you later, or just even easier by using on just some sub. Function is unstable. Is it? Or is it okay? Is it shaky?
I wasn't sure if it was my internet or yours.
Okay, it's in mine, but now it's gone. So any questions thus far? Basically, I explained how to move from this problem about integers to a problem about their generating functions. And there were these tricks of using Plancherel and using the Ofir lemma, but now we're in a position where the only thing we care about is bounding this integral. We want to show that it's smaller than square root of h. And let me check the time. Okay, sorry. Okay, so now we're going to start to bound this, and the first estimates I'm going to give you will be conditional because it's easier, but then we'll show what happens if we remove our conditional assumptions. So again, I claim that the interesting range is where we go up to h over x, and then we have this factor of delta squared outside, and we are dealing with this simplified integral. And so let us first assume for simplicity the Lindelof hypothesis. So what is this hypothesis? It tells us that zeta on the half line grows slower than any given power of t. This is as t grows to infinity. So this is completely open. We do know it for we have some concrete epsilons that are known. There is a range where it's known, but below some value of epsilon, it's completely open. But let's see why it simplifies our life. We can just, once we know that zeta is small, we can just forget about this factor and write it as h to the epsilon outside. We might need to write it as formally as x to the epsilon, but because holes prove the result for some power of h, we can actually assume that our h is at least a power of x. So I use Lindelof to throw away this factor of zeta into this epsilon factor in the power of h. And now I only have this integral of this Dirichlet polynomial m. So let's see what we get again, just for simplicity, what happens if we assume Rh. So if we assume Rh, we can actually have very good pointwise bounds on this Dirichlet polynomial, at least in some range of t. I'm not going to specify exactly the range of t where we have these good bounds, but the point is that Rh gives us essentially square root cancellation, meaning you look at the number of terms in this Dirichlet polynomial, which is essentially square root of t, and you expect this to be of size square root of d. But in fact, the coefficients are already of order 1 over d. So this is what Rh gives you, d to the minus 1 over 4. If you want to be formal, you have to throw in some epsilon in the exponent. But we didn't use the fact that we integrate. We just used this square root cancellation. And once we plug this bound of m inside and plug in this length of integration, we end up with a quantity that is essentially of the size of the variance. Again, I assume here again that d is large. D is larger than h to the 1 plus epsilon. Again, I promised you that smaller d's can be handled by some easier methods. So if d is larger than h to the 1 plus epsilon, when we assume Rh, we already have a bound that is very good and is very close to. It basically gives us the first bullet. Sorry, the last bullet in this result. Again, we have to deal with small d, but trust me that this can be done. Where were we? Yeah, so we used Rh, which is known to imply Lindelof, to get this upper bound. But I told you that if we want to get a asymptotic result, we actually want to show that in this range we have a negligible contribution, meaning we want 1/2 minus epsilon, not plus epsilon. So suppose we don't have Rh, only Lindelof. We use the mean value theorem. So what's Montgomery's mean value theorem? It's a gadget that allows us to bound integrals over Dirichlet polynomials. So let's see its statement. I have a Dirichlet polynomial of length n. I integrate it up to t. If I open it up, I have the diagonal contribution coming from alpha n matching up with the conjugate of alpha n. And the diagonal contribution should contribute t times this sum of squares of coefficients. However, if n is larger than t, we must take account of it. So the bound that this mean value theorem gives us is of t, the length of integration, plus n, the length of the Dirichlet polynomials, times this sum of squares of coefficients. So I'm not going to prove this. This is a classical result, and if you haven't seen the proof, I encourage you to read it. And once we want to apply it to our Dirichlet polynomial, so let's just remind ourselves what is this Dirichlet polynomial. So m of f plus it is this mobius d over d times d squared raised to the it. Right? Originally it was I plus sorry, it was is, but then I shifted. Then I chose this value 1/2 plus it. So we have this Dirichlet polynomial. Let's see what it gives us. So we want to bound this integral of this Dirichlet polynomial, and as I said, we have the length Ox over h. We have the length of the Dirichlet polynomial. So let's try to see what's the length. So d squared is of order d. So the length is of order d. And the sum of squares is very small because of this 1 over d. Right, I have 1 over little d squared. So essentially 1 over capital D, but then I sum it. So basically I get this bound. But this problem has a very nice feature about it. If we just use this bound, we don't get a very good result. But there is a slick way to sort of improve it, and it's to notice that this m, this Dirichlet polynomial, is supported on squares, only on squares. That's a very specific, that's really a property of the problem that we're studying. If we were studying maybe other arithmetic function, we would be stuck. But because it's supported on squares, we can just do a change of variables, divide t by 2, and then we don't change the range of integration or the sum of squares, but we do change the length of the Dirichlet polynomial. Instead of d, ta-da, we get square root of d, which is very useful. Let's see why it's useful, because this d squared cancels with this d of minus 1 over 2. Sorry, the square root of d cancels with 1 over square root of d, and we end up with this fraction, h to the 2 plus epsilon over x. And this is acceptable as long as h is smaller than x to the 2 over 3, and these, again, in this large range. So that explains how Lindelof without RH gives us this range of x to the 2 over 3. And I'll mention in 2 slides a possible way to improve it, although this is currently the best we can do under Lindelof. Okay, so this was still conditional. This is still under Lindelof. Okay. Suppose we don't have Lindelof, because we currently do not have Lindelof. So we should do some trick to control the contribution of zeta that we just got rid of. So we do Cauchy-Schwarz. So we have this integral of zeta squared times m squared. I Cauchy-Schwarz it, and I end up with a fourth power of zeta and a fourth power of my Dirichlet polynomial. Now, what's very nice about the first power of zeta, we actually know that its integral is small. So this is due to Ingham. In general, moments of zeta are very hard. There are very precise conjectures for the case moment, but we only know the second moment and the fourth moment unconditionally. So if you would choose some Holder, if you would perform some Holder inequality, I don't think it would help you. I think that doing Cauchy-Schwarz is somehow the thing you have to do here if you are working unconditionally. So what do we know about these two integrals? So as I said, the first integral is the first zeta moment. And we have precise asymptotics for it, but we don't need it. We just need this upper bound. So the upper bound is the length times log some power of log to the 4 of x, and this is due to Ingham. And the second integral, where it's just the square of m squared. So we can again apply mean values theorem to m squared instead of m. And you do that, and so the first factor here is what you get from the bound on the first moment of zeta. The second bound is what you get from the mean values theorem. I already incorporated the fact that this M is supported on squares, because we already know this trick. And it's a short calculation to see that, again, if D is in this range where it's larger than h to the 1 plus epsilon, and h is smaller than square root of x, then this will be acceptable. This is negligible compared to the expected main term, which is square root of h. So I won't have time to talk in detail how you go beyond 1/2 unconditionally, but the basic input is Huxley's large values theorem. So what's going on here? In the mean value theorem, we have this factor of n. And for some range of n, it's lossy. And it seems that that's what's going on here. If we just apply the mean value here, we get something that's off from the truth, at least in some range where h is large. But there's something else that one can do is use this Huxley's theorem. Huxley's theorem tells us something about the frequency of values of t where a Dirichlet polynomial is large. It doesn't give you the correct density, but it gives you a usable bound for the measure of the set t where this value mf plus it is larger than, let's say, 1/v. So basically, you have to use Huxley's large value theorem in conjunction with the previous tricks. And then you go slightly beyond, you go up to 11/6. Again, if you want the gory details, I invite you to read the paper, it's on the archive. Before I move on to say just a few words about the main term, I want to sort of raise some sort of open question. So we have this integral of zeta times m. And you should think of m as being somehow related to zeta, not at it, but at 2it. And you would expect that somehow zeta at it and at 2it will be somewhat independent. In fact, if you read the paper of Keating and Rudnick, that's something that goes into the proof in the function field setting. This is actually something that's known in some form. So if we would know that they are independent, and what do I mean by that? I mean that I can just write this integral as an integral of zeta times an integral of m, without doing Cauchy-Schwarz to do this separation. If we would know that, we would get a result in a much wider range. And I haven't thought, okay, I think that I have no idea how to prove this where h is very large. Let me say that. Maybe for small h, one can do something in this direction, but I don't know how to do this for large h. The larger h is, the harder it becomes to show something like that. So that's something that's missing if we want to go beyond 2/3. I allow you to assume Lindelof and RH here. So, okay, so that was everything I wanted to say about bounding the contribution of large D's. And how much time do I have left, Sarah, please?
I guess we don't have an official length for the talks, whether it's like 50 or 55 or an hour, but let's say you have 4 minutes.
Okay, 4 minutes, perfect. Thank you, Sarah. Okay, sorry. So let's summarize. Under Lindelof, we know that large D are negligible when h is up to x to the 2/3. Unconditionally, I showed you how to do it up to square root of x, and I try to convince you that you can go even slightly further. Still, we need to compute the main term. Again, I don't have time to go into the details, and this is somehow not the hardest part or the most interesting part, but let me say briefly what goes into the proof. So you have this integral. So here I don't do any dyadic dissection. I have this sum, but now I restrict my d squared to be at most capital D. And again, I subtract the contribution to the main term h/zeta of 2 that should come from these small d's. And I want to use Poisson summation because every time I have a sum over some interval, Poisson summation will allow me to replace it by a smoother sum, maybe a shorter sum. So it's very useful, but it's usually you can't introduce it directly. You have to introduce some smooth weights first. So that explains the ugly equation, because now I'm going to click and I'm going to introduce, instead of integral from 0 to x, I integrate over r, but I introduce this smooth function sigma, which you can think about as some approximation to the indicator function of 0 to 1, say. And we will require that the Fourier transform of sigma will be completely supported. And I introduce some smooth weights here also. So there are smooth weights related to x, and there are smooth weights related to m. And I don't have dx here because I don't have space, but it's dx in the end. And now we can introduce smoothing. And once we introduce smoothing, things become, we apply Poisson summation, and we see that there will be some range where it will be really easy to evaluate. So I don't give the details, but the point is that there will be some diagonal contribution, and at least for h smaller than square root of x, that's all that will be there. But if h is greater than x to the 1 over 2, there will be some non-diagonal terms that should be should be accounted for. And we are basically able to give just a bound on the number of the terms. We don't need anything about the weights, cancellation in the weights of the terms, just some bounds on their number. And this allows us to get something that can go up to 11 over 6. Again, I don't give the details because there is no time. Okay, I skipped that. And very briefly, in the couple minutes that I have left, again, we proved some result about square frees, but it's interesting to compare it with the situation with primes. So S of x is the summatory function of square frees, and psi x is the summatory function of the von Mangold function. You think of the von Mangold function, if you haven't seen it, as a funny indicator of primes. So we've seen that there is a conjecture that S of x minus x to the zeta of 2, x over zeta of 2 should be around x to the 1 over 4. We've seen that this left-hand side is a sum of square root x terms, and we expect some square root cancellation, but this is completely open. And for the primes, there is a corresponding conjecture with x to the 1 over 2 plus epsilon. This is known under RH and in fact equivalent to it. And I want to mention that under RH, people studied the arrow term in square free numbers, and they've obtained some powers that are less than 1 over 2, but still not quite 1 over 4. But in primes, we have a very elegant result that this is equivalent, this estimate is equivalent to RH. The second bullet here is about short intervals. So we expect that the count of primes in the interval of size h will be asymptotic to h over zeta of 2, as long as h is greater than some arbitrary power of x. Again, as this is stated, this is completely open, but there is some range of epsilon where this is known. For primes, we have a corresponding conjecture where it's conjectured that this difference of size is asymptotic to h, as long as h grows to some greater than some power of x. And again, this is known for some range of epsilon related to the 11 over 6 mentioned before, in fact. But again, this is completely open. If you assume RH or whatever, you still cannot go down to arbitrary epsilon. And in the last bullet, I tell you about the variance. So the variance of square frees for random starting point, we've seen that it should grow like square root of h. And in some range, we know it unconditionally. And the variance of primes should grow like h times log x. In fact, it should be log x over h, but in the range that we are interested in, log x and log x over h are of the same order. But this is completely open. Under RH, you can obtain some bounds where you have a worse power of log. But actually obtaining h over log x it's completely open unless you assume the percolation conjecture. Okay, in the next bullet, I want to sort of advertise a conjecture which is very much open, and I think hints towards this conjecture were first mentioned in works of Grimmett. So it's not a new conjecture, just not that known. So a stochastic process xt is called a fractional Brownian motion with parameter h if it starts at 0. Its expected value at each point in time is 0. And xt is Gaussian, where we have the property that the distance between xt minus xs squared should have expected value t minus s to the 2h. So if h is 1/2, this is just a usual Brownian motion. So now let us form these random processes st and ct. So st is a sum of the square-free indicator function in an interval of size th. T is the time, so when t grows, we accumulate more and more square-frees, and I subtract the main term and divide by the variance. And I do the same for c of t. And h should be thought as some fixed power of x. So I guess it's it's a folklore conjecture that c of t should tend to standard Brownian motion as x tends to infinity. And the conjecture that's somewhat implicit in some works of Grimmett is that st, this process coming from square-frees, tends to fractional Brownian motion with parameter h equals 1/4. So this somehow tells us that this somehow encapsulates the fact that s of t is that square-frees are much less random than primes. The smaller the parameter, somehow the less it can go, the less the Brownian motion can go. The condition defining it really restricts the distance between xt and xs. And we have some graphs in our paper that sort of show this Brownian motion, so you might take a look. Okay, I hope I didn't go too much over time. That's all, so thank you for listening, thank you for coming.